So, hi everyone, welcome to today's network seminar. Today our speaker is Dane Taylor. So Dane is currently an assistant professor of mathematics at State University of New York at Buffalo. He obtained his PhD in applied math from University of Colorado. Currently, his research interest includes multi-scale theory of complex net systems, networks, dynamics, and data. So then the floor is yours. Please feel free to start.
Thank you. So yeah, today's talk, I guess, is titled Homological Analyses of Network Dynamics. So the kind of overarching idea is I'll be interested I'll be presenting some recent work. You can see the 3 papers on the bottom from my group that are looking at different types of dynamics, but under this umbrella of trying to understand how the existence of cycles in networks can affect dynamics. So we'll look at a model for consensus, which is important for modeling kind of decision-making in social networks. Decentralized machine learning algorithms and AI algorithms often involve some kind of consensus model. I'll be looking at limit cycles for stochastic, basically a Markov chain, but we'll look at an application with modeling molecules or a polymer, and then information spreading and spreading of cascades in general over spatial networks. So it's a bit of a survey of kind of related things going on and how we can use homology to think about how cycles, structural cycles in a network affect dynamics. And a lot of these models will be generalized models. So I'll be thinking about a simplicial complex rather than a graph. All right, so let's jump into the first project. So we're looking at consensus defined over simplicial complexes. So consensus is widely used to study decision-making for humans, animals, and machine learning. As I mentioned, you know, your group there at Oxford is kind of leading, I would say, the extension, some of the extensions of consensus to hypergraphs and generalized notions of networks. So we're going to define a model for consensus where states are being assigned not only to the vertices, but the edges, as well as potentially higher dimensional simplices. And so in this case, I'll focus on one-dimensional simplices, which are edges. And we'll think about edges having states, and they're going to be reaching consensus through a model. And edges can be either lower adjacent to other edges, meaning they share a node or a vertex or a zero simplex, or upper adjacent, they are kind of 2 edges on a 2 simplex or 2 edges of a triangle. So let's define an abstract simplicial complex. Here it's defined just by a set of k simplices, where if k is 0, that's the nodes, k is 1, the edges, and then triangles or 2 simplices. And these are, you know, interpreted as geometrical objects. So the dimensionality of the vertex is 0, dimensionality of the edge is 1, and that's where the k is coming from. And then an abstract simplicial complex would be the union of all these k simplices. If the vertices are located in a metric space, so they have locations, then it's just a simplicial complex. So we're kind of focusing on the abstract simplicial complex, so it's not embedded in a k-dimensional space. So in this example, we can define the 0 simplices. There's 5 of them. The 1 simplices are just the set of edges, and then the set of triangles. We can equivalently define the simplicial complex with a set of boundary matrices, which define the connectivity between say the vertices and the edges. Each edge is given an orientation, and it's not a directed edge, but it is given an orientation essentially for naming And the default is to just have the lower adjacent or the lower index come before the upper index. Then it's kind of easy to keep track of the orientation. If I switch to 1, 0, then the orientation switches and it's interpreted as the negative orientation. But we can define the connectivity between vertices and edges in a boundary matrix B1, between the connections between edges and two simplices in this boundary matrix B2. And then here the sign is just indicating the orientation. So, 0, 1, 0 is the start, 1 is the end point of this edge with this orientation. So the boundary of the edge would be defined as vertex 1 minus vertex 0. So here's just some examples. We can also define the faces. So the faces of an edge would be the set of the two vertices on either end, and then the boundary is kind of assign those with an orientation. So yeah, the faces of 0, 2 would just be these two vertices. The faces of this 2 simplex would be 1 simplex 0, 1, the simplex 0, 3, and then the 1 simplex 1, 3. So just the kind of, the outer edges of the triangle. Okay, so you probably have come across this boundary matrix. Usually it shows up when we study effective resistances for graphs, but the higher order boundary matrices are useful when thinking about simplicial complexes. You can also, there's ways to kind of introduce weighting into the boundary matrices, but we won't do that. So unweighted. But yeah, there's also the definition of a coface. So the coface of an edge would be any two simplex it's connected to. The coface of a vertex would be any edge it's connected to. So the face is kind of going down in the dimension, and then the coface is going up in the dimension. Okay, so given these boundary matrices, we can define a generalization of the graph Laplacian that's known as the Hodge Laplacian. And it's the kth, it's indexed by k, where we have kind of the outer product of the boundary matrix and then the outer product of the boundary matrix, a dimension up. So if k is 0, if k is 0, then we just have this k plus 1 transpose. And so this is exactly the normal graph Laplacian. So it's an exact generalization of a graph Laplacian. And so you can think of the graph Laplacian as describing coupling between vertices. And then L1, we go up a dimension. We can think of it as encoding coupling between edges. So this is encoding which edges are lower adjacent through a common vertex. And this matrix encodes edges that are upper adjacent through their kind of sharing their two sides to a triangle if they're upper adjacent. And we will use the Hodge decomposition. And this is one thing that's nice to define with the Hodge Laplacian. So it separates a vector space, or if we think about a function being defined on, say, the set of edges, those would be, each function would be a chain or a one chain, because edges are one dimensional. So we can think of the space of kind of real valued one chains, and we can separate that vector space into three orthogonal components. One is the image of, the first boundary matrix, the image of the boundary matrix, a dimension up. And then we have the kernel of that Hodge Laplacian. And for this, talk, I'll just focus on the one Hodge Laplacian. So I just need to look at these two boundary matrices. And when we select k equals 1, we'll describe these subspaces as, the original vector space, Rm. If we have m edges, then we have this gradient subspace, the curl subspace, and the harmonic subspace. So the gradient subspace, so I can take this I can encode the any function that's defined on the edges. I can encode it in a vector, and then I can project that vector onto these three subspaces. And so I'm showing those projections here for this example. And there's some intuition on what these subspaces mean. So the gradient subspace sums to 0 along any cycle. So if I sum around this at symbol, we have the 0.045 plus 0.066, and then it's minus 0.111 because the edge is, if I'm going counterclockwise, this edge is pointing in the wrong direction. Here, the arrows are showing the orientation of the edges, but the edges are undirected. Okay, so that's the gradient subspace. The curl subspace, it's basically we have balanced flows around two simplices and then zeros for edges that are not on two simplices. So you can see that here, there's a bunch of zeros. And then around the two simplices, there's a cycle here, there's a cycle here, and there's a cycle here. So here, there's essentially a counterclockwise flow of 0.071 is one way to interpret this function that's defined in that curl subspace. And the harmonic subspace you can think of as whatever's left over. And that's essentially how we numerically compute them. So we can, project onto the image of this matrix, project on the image of this matrix, and then examine what's left over, and that will be in the kernel. Okay, and what's important here is the harmonic subspace is isomorphic to the homology. So here, of the simplicial complex. So here there's three cycles that are basically these paths that are not filled in. And so the harmonic space is a three-dimensional subspace. And here, the curl subspace, it's going to be, the dimension of the curl subspace is the number of two simplices. So there's three of these filled in triangles. Curl subspace is a three-dimensional subspace. And then the gradient is, whatever's left over after you subtract those dimensions. Okay, so this is a lot of background. I like to introduce homology in this way, first going to the Hodge Laplacian, because this is kind of how I've thought about eigenvectors of the normal graph Laplacian for a long time. So I think it's pretty intuitive. So if we talk about zero-dimensional homology, it's essentially studying connected components. And we cannot kind of understand why there's a one-to-one correspondence between connected components and the zero-dimensional homology. And we can also understand that by looking at this graph Laplacian, which is the zero Hodge Laplacian. It's the same matrix. So we probably know the number of eigenvalues of the graph Laplacian is equal to the number of components. And we can also think about that as the kernel. So if we think about, the space of n-dimensional, this should be m-dimensional for m edges, and we can separate it into two orthogonal subspaces, the image of the Laplacian and the kernel. The kernel is just the set of vectors such that, L0 times a vector equals 0. And for this graph Laplacian, they all take this form. It would be a vector of ones. But if we have three components, we can have three such vectors where it's, a constant on one component and then 0 on the other components. And so we can see here, there's, in this example, three components, and we have three such vectors. So there's a three-dimensional subspace. And so we can kind of understand that the dimension of, or I guess the zero-dimensional homology is three-dimensional in this case. Okay, so the Hodge Laplacian generalized is this. So we can look at the kernel of the Hodge Laplacian in one dimension, and it's basically going to, the dimension of that kernel is going to coincide with the harmonic space, which coincides with the homology. So here there's, three cycles that are not due to being the boundary of a two simplex. So the kernel of L1 would be three-dimensional subspace, and any vector in that subspace will be in the harmonic space. There are cycles that are the boundary of a two simplex, kind of by default. And so the homology is defined as the subspace of cycles that are not containing cycles that are the boundary of two simplices. So it's this quotient space. So that's defined in the one-dimensional homology, but we can define, the k-dimensional homology as well. All right, so let's use this for an application. We'll look at dynamics. We'll look at consensus, and we'll define consensus using a balanced Hodge Laplacian. So this is basically a Hodge Laplacian, but I use a scalar alpha to kind of tune the relative contribution of these two matrices. And then I define a linear dynamics. If L1 was L0, this would be a pretty traditional model for consensus. But now I'm changing and replacing this graph Laplacian with a one Hodge Laplacian. So this is consensus where we have coupling between the edges, and each edge is given a state. And when alpha is close to 1, consensus is more strongly influenced by lower edge-edge interactions. So edges that have a common vertex. And when alpha is close to 0, the consensus is more strongly influenced by the upper connections. So when edges share a triangle. Scaling by alpha has no effect on the Hodge decomposition because just due to the orthogonality of the subspaces. And we can use that orthogonality to think about what solutions are, and there's a decoupling of the solutions, or I should say the Hodge subspaces are invariant subspaces for the consensus dynamics. So if I take some initial condition, or I take any state where xi of t is the state of edge I, and I can decouple it into those three components: the gradient component, the projection onto the curl subspace, and then the projection onto the harmonic subspace. And I can think about the action of the Hodge Laplacian on each of those components, where these components are satisfy this property here. So the curl component's orthogonal to the B1, the gradient's orthogonal to B2, and the harmonic is in the kernel of L1. So we can use these properties and see there's a lot of cancellation. And essentially the systems decouple, so we can study, the gradient component evolves according to its own differential equation, which has this pretty simple solution. Curl component evolves and has this pretty simple solution. And then the harmonic component, we can see both those terms cancel. So if we look at the derivative is 0. So the harmonic component doesn't change. But we can, oops. Okay, so what this means is dynamics converges on the gradient and curl subspace. Dynamics is unchanged on the harmonic subspace. So if we have this initial condition, I can project it onto the three subspaces and simulate the dynamics. And we can see the gradient and curl subspaces both converge. Harmonic subspace, the projection onto the harmonic subspace doesn't change. So the total basically converges to having this function be equal to whatever's in the harmonic subspace. And we can think about this if we step back and think about the role of homology in this dynamics. Because homology is isomorphic to the harmonic subspace. So if we think about in the traditional setting of consensus, we're in this scenario where we're looking at consensus model here with the graph Laplacian, just the traditional graph Laplacian. Here we would have, each node or each vertex has a state. So this would be, a 6-dimensional vector space. That's the possible states that the model could take. And if we study this consensus model on this connected graph, the states X will converge to some point along a 1-dimensional subspace, which is the harmonics subspace of L0. So it's a 1-dimensional line. And so this point here, if the system has some random initial condition in this 6-dimensional space, it's going to converge to this point, which represents, the mean, or what is the the system will reach consensus at the average value. So this is kind of the traditional setting for when one defines a consensus model. But you could ask, what happens to the consensus dynamics in the traditional setting using a graph Laplacian if you have 2 components? Well, the possible solutions is now a 2-dimensional subspace, depending on what the initial condition is for the vertices in this component and the initial condition for the vertices in this component. When the system converges, it's going to be converging to some point on this 2D plane. If you have 3 connected components, you simulate consensus, it's going to converge to some point in this 3-dimensional subspace. Each of these subspaces are interpreted as the 0-dimensional homology, or the 0-dimensional, the kind of the harmonic subspace in dimension 0, where functions are defined on the vertices. So we can see how in the traditional setting, defining consensus for when vertices have states, this is typically what consensus is being implemented. And then if you have different connected components, the homology space grows in dimension, and we can have different solutions that are converged to. So then now let's move over to the 1 Hodge Laplacian and study this consensus model with the 1 Hodge Laplacian. If there are no cycles like this simplicial complex, the system will converge. The 1 homology, 1-dimensional homology is just a 0-dimensional subspace. It's a point. So everything will converge to a single point, just like in the traditional setting of consensus, or in the definition of the word consensus, everything reaches the same limit. If we have a cycle, the system will evolve to some point along a 1-dimensional line. If we have 2 cycles, the states will evolve somewhere in this 2-dimensional subspace. These different trajectories being shown here are just 3 different initial conditions. And the same over here. Different initial conditions will bring you to the appropriate subspace. And that's the linear dynamics that plays out. So yeah, essentially, we define this consensus model, and it's going to converge to a subspace that is the harmonic subspace. We can interpret it as being isomorphic to the homology. The next thing we did in this project was think about the rate of convergence. So if this initial condition is converging to a subspace, what's the rate of convergence? Since the solution decouples, we can have a convergence rate for the projection onto the gradient subspace and the projection onto the curl subspace. So we have lambda 2, 1, lambda 2, 2. They're the smallest non-zero eigenvalues of these 2 matrices. And then the overall convergence rate is just kind of the slower of those 2 subspace dynamics. So that lets us optimize the coupling. And so we set the convergence rate to be the same for those 2 subspaces, which lets us find alpha star. And so this is the optimal balancing parameter where convergence is the fastest. And to just hop back, since I didn't show the equation, oops, here, this was our definition of the Hodge Laplacian. So we're just balancing this matrix and this matrix, and we found an optimal value of alpha star, where the system converges as fast as possible. Okay, so that's just showing the convergence rates for this simplicial complex here. This dashed line is kind of what we find to be the optimum. And then if you're below it, the gradient subspace converges more slowly. So that's up here. And then the convergence of the entire system kind of matches that of the slower system. And then when alpha is above, the curl subspace is the bottleneck, converges more slowly. The slope of this line, here I'm plotting the error with respect to the final value. So when you're above alpha star, the curl subspace is converging slowly, gradient subspace converges fast, but the whole system converges kind of with that slower subspace. Okay, so this can be useful. The applications for this are a little abstract. I think the more useful applications are a little downstream, thinking about, well, consensus is already used for neural networks and developing decentralized machine learning. And so that's kind of what I'm thinking as the future applications of this model, since it is a little bit abstract. And there's growing interest to develop neural networks with simplicial complexes instead of graphs. So that's the application of this. I have, that's the end of part one. So I have this kind of pause point. Are there any questions on what I've discussed so far?
I would say no. We can move on, I guess.
Okay. Yeah, and if anything's not clear, or if you have questions, please just go ahead and chime in. Okay, so now we're switching gears a little bit. I'll be talking about the use of persistent homology to study convection cycles with network flows. So here we will use homology to automate the detection and summarization of cyclic patterns for irreversible Markov chains. So Markov chains are used in many applications, developing stochastic models of them in biology and physics. And I'll look at a physical model later where we're looking at polymer growth. So you have a polymer, which is kind of a sequence of molecules, and you can add a new molecule on the end. And so that's growing, or one of those molecules on the end falls off and it's getting smaller. So you have some stochastic dynamics for the growth and kind of decay. And then you have a polymer, it can fold, it can do weird kind of shapes of orientation. So you have configurational changes or conformational changes. And so you can develop a stochastic model for those changes. So we'll look at this polymer model, a Markov chain model of polymer, as well as PageRank, which I'm assuming everybody knows pretty well. Okay, so I talked about homology, which is essentially the space of cycles. And we can define persistent homology if we have a filtered simplicial complex. So instead of just having a simplicial complex, we define a filter, which basically is going to let us define a nested sequence of simplicial complexes. So you can see this example here. I have a bunch of vertices that are uncoupled, and then I start adding in the one simplices, or the edges, and then eventually add in these two simplices. So I have this sequence of simplicial complexes, and it's nested. So I'm only adding in k simplices as we do the filtration. And so for each one of these, I can identify the homology. So here I have, 7 vertices. So that's 7 connected components. And there's 1, 2, 3, 4, 5, 6, 7 kind of bars representing those 7 connected components. Here I'm looking at this weighted graph, and I'm adding in edges according to the edge weight from largest to smallest. So the first one that shows up is this because it's a weight 4 and that's a weight 4. So at this filtration parameter epsilon, when it hits 4, then those 2 edges show up. And I keep doing this, I get down to 3 and this edge shows up. And that edge shows up. I think there's a discrepancy between this picture. I need to update that with the 3, it looks like. But you can see that edges are showing up and then the 2 simplicities are showing up. And then we could just keep track of homology as the filtration occurs. So here, there's these edges. So we say that these 2 components die. And so instead of 1, 2, 3 components, we now have all 3 vertices are in 1 connected component. So 2 of those connected components have died, which are represented here. And then eventually an edge goes out to this vertex here. So that no longer is a separate connected component. Once we get here, these 4 are in the same connected component. So this connected component has died, and that's indicated here. So you can think of a persistence diagram here. It's tracking the homology as it's evolving or as it's persisting during the filtration. And there's a continuation here. So, we can represent the homology with homology groups, and those homology groups remain the same throughout that filtration. And they're either dying or they can be born as well. So here, if we look at 0-dimensional homology, 1-dimensional homology, we see a cycle is born right here. A, B, C, D is this, or no, yeah, A, B, C, D is this cycle, is born right here. So that there's a generator for that homology, which you can think of as a cycle or a chain that represents this. It's probably just A, B, C, D. So this edge, this edge, this edge, this edge defines that cycle. And it's born here. That means at this value, if we looked at the Hodge Laplacian, if we looked at 1 Hodge Laplacian at this value of epsilon, those 2 edges appear, and the 1 Hodge Laplacian, the null space would now be a 1-dimensional null space. The harmonic space would be a 1-dimensional subspace. Okay, so this is just tracking the evolution or the persistence of homology and the homology groups as we vary this filtration parameter. We're doing the filtration here by defining a function over the set of edges and then just varying a threshold, keeping the largest values first. And so for each graph, we consider the clique complex, which basically says, if there's a triangle, fill it in and add the 2 simplex. Okay, so we're going to use this technique to understand and study convection cycles for network flows. So I introduced an approach where we consider a stationary distribution for, I'm just looking at the random walk, discrete time random walk. We have the stationary distribution over the nodes. And then for each edge, I can define the stationary flow across an edge, which is just the stationary distribution times the probability Walker goes from I to j. So that's the stationary flow across I to j. Then identify the imbalances. So where is the flow larger from I to j than j back to I? And I encode that in a delta. And then I take the absolute value of delta and I define that as the function on the edges. And I can do the filtration of this flow imbalances. Here I'm indicating the arrows just to indicate the direction of flow imbalances. I applied this to look at the page rank. And what we find essentially, the transition matrix is the page rank matrix. We have the teleportation parameter defining kind of all-to-all coupling, and we can vary that teleportation parameter to between kind of this case where alpha is 1, and then this case where alpha is 0, the graph would just be all-to-all coupled. And I already showed the persistence diagram for the flow imbalances. And basically, the persistence diagram is just summarizing the homology of these convection cycles. And if I vary the teleportation rate, say I decrease it, you can see, and I'm studying the persistence diagram as we vary the teleportation rate. The persistence diagram changes, meaning these convection cycles change. And essentially what's happening is teleportation is imposing a regularization on homology. So we can see that here. In this case, we have this cycle A, B, C, D, which is the first cycle that shows up. So if we're keeping just kind of the strong cyclic flows, this is the largest cycle. But as we have more teleportation, eventually when alpha drops down here, if you do this filtration, you'll see, cycle A, B, D, A, and you'll see cycle B, C, D, but you'll never identify this large outer cycle that includes A, B, C, D back to A. This cycle no longer is significant. So when we look at the persistence diagrams, and we track, originally this was the most significant cycle. As alpha decreases, that cycle disappears completely. So that's what I mean by regularization. When we introduce the teleportation, it perturbs the transition matrix so that the stationary flows are less cyclic, essentially. And we can capture that to find a bifurcation diagram. I'm just tracking the kind of the start and the stop, so the birth and the death for each cycle. And here there's a bifurcation that occurs at this line. Here I'm plotting just the page rank values. The bifurcation seems to kind of correlate with, I guess, this kind of switching of the page rank order, but that, I don't know, it's more of a loose correlation, I would say. I will point out there's a little bit of a difference between a graph theoretic notion of a cycle, which we can think of as a directed path that comes back to itself, and then a cycle in terms of homology. So when we're studying homology, we're essentially ignoring the edge directions. Although here I'm showing them just to make the comparison a little bit easier. So in this case, if we look at this, we can identify these 5 cycles. And so these are paths that come back onto them, start and stop at the same location. You can kind of convince yourself that each of these cycles comes from up here somewhere. We don't track this cycle because we consider a clique complex, and so we fill it in with this 2 simplex. So it's not in the homology space, it would be in the curl subspace. So we're not tracking that cycle. And so there's a one-to-one correspondence between what we find with persistent homology in these cycles. But once we have 2 simplices, it's a little tricky. So these 3 cycles in terms of the homology are equivalent. It's the same generator. So when we talk about a homology cycle, we're not talking about a path that comes back to itself. What we're talking about is a whole. So because these 2 simplices exist in the simplicial complex, the clique complex, these paths identify this whole. and all three of these paths identify the same hole. So these are equivalent generators for this hole, this one-dimensional hole. It's a one-dimensional hole because we can bound it with a sequence of one-dimensional simplices or a sequence of edges. We'll go around that hole. So comparing kind of cycles in a graph to homology in the notion of cycles, which is defined as a hole, it's a little tricky and kind of an open technical direction that needs more work. I'll just cover a quick application. We looked at polymer dynamics, where a polymer is growing and decaying and has different configurations. In this case, we can represent all these stochastic transitions in a two-dimensional lattice. And what happens here that's interesting is when the transitions are much higher external transitions versus the internal kind of transitions, the system localizes onto this outer path. So what happens is, with high probability, if you have a random walk, or it's going to move to the edge and it's going to stay on that outer boundary. And so the stationary distribution localizes to the outer edge. It's an emergent property. So we capture that with these persistence diagrams. There's some connections here to the quantum Hall effect, similar models with this 2D lattice, as well as some models for, this is one way you can kind of model how a biological system has short time scale molecular dynamics, but then a large population of biological processes can give you kind of a large scale cycle in terms of the dynamics. Like a circadian rhythm is on the time scale of 24 hours, whereas the molecular dynamics involved are kind of milliseconds or faster. Okay, that's part two. I realize I'm basically out of time, but maybe I have a third part. I'll stop. I can go over pretty quick or skip it, whatever you guys are thinking if there's questions.
Do you have any question now? I guess you can briefly go over the screen. We do have several minutes. Yeah.
Okay. I'll do that. For this third part, I guess it's pretty relevant. So this is built out of work with some people at Oxford back in 2015, and then we're extending it now. And we're basically looking at spreading processes over spatial networks that have both short range and long range connections. So this is roads in the metro in London. And if we simulate a spreading process, there's two spreading processes for basically rumor spreading that requires social reinforcement. So this is the Watts threshold model. When the threshold is high, the cascade cannot jump across a long range distance because there's no local reinforcement. So the spreading spatially is going to be pretty slow. And it's going to, on the right hand side here, it propagates along a 2D manifold, the 2D plane, as a wavefront. On the left, when the spreading does not require social reinforcement, a person can get on the metro, go across town, and the spread can jump spatially. This is also important for epidemics, this kind of spatial wavefront propagation versus the jumping appearance of new clusters, relevant for kind of how an airline network impacts the spatial spread of an epidemic. But this is on a more fine scale, just within the city. So we're going to study this phenomenon. Whoops. So we have these competing properties. The spread can jump along a long range edge to make a new cluster, or just a wavefront can kind of propagate locally. And you can see there's different spatial patterns. What we do is define for each node the time at which it first becomes active, or the time at which it first becomes infective. And so this gives us a matrix of activation times. And we can use that to embed a node, or the set of nodes, we can embed them as a high dimensional point cloud. So for each node I let Yij be the time at which node I activates when the cascade starts at node j. So this maps the node I to a vector. So when does it become active? When the cascade starts at node 1? When does it become active? When the cascade starts at node 2, and so on. So this is kind of a vector, a feature vector that describes how node I is connected into the rest of the graph. So we can think about a contagion map is defined as a nonlinear mapping that embeds a graph into a high dimensional metric space. When the graph has a manifold, so like this small world model where nodes are located on the outside of a ring, then the point cloud potentially will also contain this manifold structure. So what we proposed in this work was we can study manifold structure in the point cloud, and that tells us the extent to which the cascade is spreading along the manifold using wavefront propagation. And when there's not this, when there's not manifold structure, that means the cascade is jumping across long range connections and we don't see the wavefront. So the manifold recovery in this embedded point cloud allows us to quantify, which phenomenon is dominating, this wavefront propagation or the long range spreading. Contagion maps have been extended recently. These guys, Barbara and Florian, I think Florian may be still at Oxford. Barbara graduated last year. It's 2 years ago. Thanks. So yeah, oh, here we go. So in this preprint, we extend the Watts threshold model to simplicial complexes, develop some bifurcation theory. So we're calling these simplicial cascades. We study them on noisy simplicial complexes, which we generalize or introduce as a generalization of small world networks. So instead of kind of short and long range edges, we have short range and long range simplices. And then we introduce simplicial cascade maps that allows us to, instead of embedding a graph as a set of points in a metric space, we embed a simplicial complex as a set of points in the metric space. So I think I'll just kind of skip the model, but I will just point out what we do is we define vertices to be active or inactive, edges are active or inactive, two simplices are active or inactive, and then we define a simplicial exposure, accounts for each vertex, the neighboring vertices, the neighboring edges, the neighboring one simplices, the neighboring k simplices, what fraction of those are active. And then we kind of have this effective exposure that accounts for all of the simplices of different dimensions. Yeah, when there's only interactions through edges and two simplices, we use the delta to measure two simplex interactions. So generalizing this idea of wavefront propagation, when you have a simplicial complex, the cascade can follow what we call a geometrical channel. So a geometrical channel generalizes the notion of a path. So instead of an edge connected to an edge connected to an edge, we have a two simplex sharing an edge with a two simplex, sharing an edge with a two simplex, or we have a three simplex sharing a two simplex with another three simplex, and so forth. So it's kind of these a sequence of, I define it here, non-intersecting sequence of lower adjacent k simplices. So there's a lot of different dimensions. The Cascade model can have a dimension. The simplicial complex has a dimension. This channel, you can think of it as a channel width, or it has a dimension. And we have some bifurcation theory to describe the kind of whether or not there's wavefront propagation. The main thing is here, when the cascade spreads, and it's mostly influenced by two simplex interactions, so higher order interactions, this significantly promotes spreading along geometrical channels and suppresses spreading across long range connections. So that's kind of the punchline. We use persistent homology to quantify this, which is a Votoris-Rips filtration, to ask, this point cloud, we want to quantify the extent to which it has lies on a ring manifold. So we can use persistent homology to do that. And yeah, essentially, our bifurcation theory predicts when the ring manifold is recovered in that kind of embedded. So I'll just jump here to the conclusion. Yeah, essentially, thanks for your attention. I wanted to survey kind of 3 application areas. We're using homology to study dynamics over networks, and mostly looking at kind of generalized dynamics over simplicial complexes instead of dynamics over graphs. Introduced a model for consensus, and found that we could balance kind of some subspace dynamics to optimally accelerate consensus for functions defined over edges. We use persistent homology to automate and summarize the detection of cyclic flows in Markov chains, which we could summarize in these persistence diagrams. And then I introduced simplicial cascade maps that use a simplicial cascade. So a threshold model cascade spreading over a simplicial complex. And we could use persistent homology studying this kind of latent embedding. So we embed the simplicial complex as a point cloud, study the homology of that point cloud to understand the extent to which cascades spread along the geometrical channels. Okay, so this work was led, those 3 projects were led by these 3 students. I have asterisks on Cameron and Olgan, who will be on the job market next year. And the papers I discussed are here. So I'll stop there. And if you have any questions, I'd love to answer them.
Very interesting talk. Do we have any question from the room? Yes, Steve, please.
Thanks, Dave. I was wondering, it's a general question about persistent homology. Does it ever make any sense, or does it not work the theory to have something like persistent homology, but where edges are appearing and disappearing, or does it always have to be that your edge function is like strictly increasing in terms of the number of structures that are being added as the threshold changes?
So good question. There's something called zigzag homology, which I've never looked closely at. So maybe that does it, and maybe it doesn't. I really don't know. Everything I've looked at, really, to be like a filtered simplicial complex, it has to be kind of, you're always adding, so that it has to have this nestedness property where it's always growing. So yeah, you can look at the zigzag persistence. I think it's different though. I don't know. I see some nods. You guys probably know better than I do if you've looked at it. Yeah, but so I would say no from what I know, but it's possible.
Thanks.
Yep.
Thanks. Anyone else? No.
That's still my question. I
I also don't see any questions online. I'm actually wondering your model like the extended model of Watts model for the cascading you mentioned at the very end. I wonder how the one complex, a simplex, interacts with two simplex, because there's some reinforcement needed for the Watts model, right?
I didn't exactly, well, understand the question.
Yeah.
But if you could repeat it.
Yeah, if you can go to the next slide, you have like one simplex, two simplex. The node, the edge can be active and inactive. Maybe next slide. Oh yeah, here. So it's like, if we want a two simplex to be active, do we need like two active simplex to do that? Because there's some reinforcements needed in the Watts model, right?
Yeah, so I definitely skipped over this. So we define, how do we define the model? Essentially the interesting dynamics is happening to the vertex states. And then the one simplex and the two simplex states are kind of trivial. We might extend that in future work, but like we define a k simplex if k is larger than one. It's active if k minus one of the vertices are active. So if an edge becomes active, if one vertex becomes active,
Okay.
a two simplex is active immediately when two of its vertices are active. So we could have gone the other route. So this is kind of like the highest threshold for activity.
Yeah.
But we also define it, the higher dimensional simplicities are immediately active. So we could have like a time delay, or we could have, you know, additional equations that describe,
Yes.
allow more complicated behavior for the high dimensional k simplices. But in this case, they're just kind of deterministically defined as soon, depending on what the vertices do. And then the interesting dynamics is with the vertex activations. So I think I needed to add another bullet point here that says, just like the Watts threshold model, when the simplicial, when the exposure surpasses the threshold, the vertex becomes active.
Okay. Yeah. I see.
So when this is greater than tau, then the vertex changes.
Thanks.
Mhm.
I have a question.
Yeah,
So
please.
on your second approach, on your the second method you explained to us, there's this parameter alpha or epsilon of the filtration. Did you study how do you increment or what's the rate you change it? For instance, because the edge value, the real value. So does it affect how you change this parameter?
So this model here.
Yeah.
So here so the dynamics is, yeah, so alpha is the teleportation parameter. And I don't think, so yeah, let me stop back. So I simulate the kind of random walk to the stationary distribution. Well, I just compute it analytically, and then I find the flows. So the system's always in kind of stationary state. And all I'm doing is changing the transition matrix that I use. And I just selected a few alphas for that teleportation parameter when defining the, I guess, the Google translation matrix. So I'm not really varying alpha as part of the dynamics. And I just selected some values of alpha. So it's possible, like, yeah, maybe at 0.7 or 0.71, I've missed something. Maybe there's some kind of homological feature that appears and disappears real fast. But I guess here I'm sweeping about 100 values of the alpha. And they're just kind of calculated independently for each separate alpha. And I'm, yeah, it doesn't seem like I'm missing something, but it's possible. There's also a stability theorem for, it's called the nerve theorem for when you're doing a filtration. So this is something, you know, that could be proven. So if you do a, let's see, you know, I could take the derivative of P with respect to alpha, pretty straightforward. And then I could consider the stationary distribution and take the derivative with respect to alpha, which is also pretty straightforward. And then I could, you know, define how, if I change alpha, what the change to the F is. So P changes, pi changes, F changes. And I think that's a continuous, it would be, F would vary continuously with alpha. Looking at the product here, maybe it's like, you know, alpha squared. It's like the lowest order term might be a quadratic, but it's still continuous. And so the nerve theorem would say if the function just changes slightly, right, you can define an infinity norm on the function change. So, you know, if I figure out the perturbations to F and do an infinity norm, then the persistence diagrams, each kind of birth and death location is just going to be changed, but and bound by that infinity norm. So any functional change, so like if I change this to 1.1, then these are only going to change by max like 0.1. So the homology is basically robust, and the persistence diagrams or these barcodes are robust to perturbations of the function. So that's something that could be done to kind of analyze the sensitivity with respect to alpha.
Right, thank you.
Mm-hmm.
Thanks. As it's already 3:05, I guess that's the end of our seminar. So let's thank Dan again.
Thank you for the invitation.